So hello, I'm Ari Kulmala, Principal Associate Architect representing TII. So first I will be running through a little bit of introduction of who we are. So Technology Innovation Institute is based in Abu Dhabi, doing applied research, world-class R&D on actually many different research centers, which we don't go over here to the time, but we are representing the Secure Systems Research Center, which obviously means that we are very focused on the security topics. We do a lot of work with different ecosystems, obviously with the RISC-V, also where you might have seen us active, and then we have loads of partnerships around the world with the leading universities, mostly in the US and EU. But then what we are actually going to talk through now is the what we are working in the hardware domain, mostly in the hardware domain. So we are building this kind of end-to-end systems with drones. We have edge drones, we have fog drones, and these are controlled from the cloud. So we make this whole system to work. We are, like I described, we are the we do this kind of applied research. So we actually want to put our stuff into practice and test it with kind of like true software that do our assumptions hold. And here from the SOC perspective, we are mostly interested in the drone side, not the cloud side. So with flight controller, mission computer, kind of chips that have different requirements. Mission computer requiring a little bit more performance due to it needs to execute the AI ML kind of tasks like object detection, object avoidance, etc. for the autonomy of the system. But like I said, we are thinking this from the security point of view. So there are actually a lot of existing threats and mitigable threats first that we need to take into account first in the hardware domain, of course, because you need to have the hardware reliable and secure in order to be able to do that for software. So I'll show the mitigations here also at the same time. But like you see, there are user system software based attacks, protocol attacks, cryptography attacks, basic hardware attacks, all the side channels, etc. Fault injections. You can spoof the sensors. You can attack through different supply chains like the hardware supply chain, but also the software if you're using open source software, etc. So we need to address all of these challenges. And thus we are building our own SOC platform with various partners, as you can see from the slides, based on open source. We call it Saqr. And there we are extending what the open source currently has to offer, like we are using the root of trust based on OpenTitan, but we need to add and extend it, for example, to be able to offer crypto services for the host processor, as well as we need to add support for PMP MMU. Then we have on our description of the IO MMU, implementing extra instructions to prevent from Saqr meltdown type of attacks, and logic locking for supply chain. So the Saqr looks like this. It has a host CPU subsystem with dual core Ariane CPU, interconnect with loads of peripherals, so all the sensor needs are basically covered there, so SPIs, I2Cs, etc. Then the security subsystem, so root of trust, like I said, based on OpenTitan, but then extended to have secure mailbox, PUF, physically unclonable function, etc. And the parallel programmable accelerator is used for the mission computer kind of tasks. So that's the AI type of accelerator. Then the threats in the software. So when we have the hypervisor or hypervisor extension already in our chip implemented, we have actually 3 different kind of operating systems that are are running on top of the BAO hypervisor, and we can use the hypervisor to protect the memory access, for example, between the virtual machines, or like enabling the isolation. Then naturally we need to implement all the software services for the hardware that has been implemented, so key storage, end-to-end encryption, provisioning, secure boot, firmware updates. And then overall we are using the global platforms API to provide these security services. So this basically is the base that we have now for the our what we have existing, and we actually have the first version now in our lab, and then this is about to tape out. But maybe the most interesting part is that where we are going now, and that's the what we call zero trust research. So what it actually means is that you don't, in the end, trust the actors of the chip. Even if you try to design an unhackable system, somebody's going to find a way to go in, and you are kind of like prepared to that there will be a breach. Even if you do the best you can, somebody sometime will find a way to go in. So you try to mitigate what he can do there. You try to mitigate the accesses so that the kind of like all chip and platform secrets are not going to be exposed. You want to make it a very tedious task, and so that even if you break one chip, the same attack is not going to kind of like give you keys to open all the chips, but you would need to do the same tedious job for each of the chips that there are, and you want to be kind of like securing the platform throughout the whole supply chain. So for instance, for the supply chain security, we are implementing this kind of a logic locking feature, which will lock the chip so that there won't be any unauthorized usage without the chip being explicitly enabled. What else we are researching, and this is really like in the forefront of the new security technologies. So the confidential computing, machine learning based control flow integrity, so that you can see that if there is actually somebody trying to hack your code, having something running on the CPU that is not supposed to be running, or mysterious branches, stuff like that. Platform-wide GE. Then we are also looking at Cherry. We today heard from Codasip that they have Cherry-enabled CPU available. We are still considering the pros and cons of Cherry, for instance, in the terms of hardware usage, etc. Interestingly, we are also applying large language models. So we are reading the security specifications by AI and utilizing what it learns from the security specifications to the implementation of the security. That does it actually fulfill the requirements of the specification. So it's on top of the typical verification that you would be doing, and we have been actually able to find some good stuff with this approach. So I think it's very promising. IP peripheral authentication, so that you can actually be sure that nobody's changing the chipset itself, but the chipset is kept safe and stable. Working with side channel resistance and runtime assurance, meaning that during the runtime also for security you are trying to monitor that nothing that is not supposed to happen is happening somewhere, and if you see something, then you are going to shut down the chip and trying to put aside the infected malicious parts of the chip. Supply chain security I already told, and then going back to being the practical research center. So of all of these, we have a pipeline of research chips that we are going to produce with the new features, building the software on top of those, getting the new learnings, and continuing this track. And we actually welcome partners to work with us also. We already have quite a big partner network, but we are always open to any new contribution as partners. And that's all. Thank you.